Question 2 from the 2023 Advanced Higher Physics Examination from the SQA. A student is investigating rotational motion using the circular plate in a microwave oven. It's shown in figure 2a. The microwave oven is switched on and the plate rotates with an angular velocity of 6.2 revolutions per minute. And we've got to show for 2 marks that the angular velocity of the plate is 0.65 radians per second. So this question is all about changing the units of revolutions per minute into radians per second. It's a unit changing question. So we start off with 6.2. I'm going to say it's going to be 6.2 revolutions per minute. And that's where I'm going to write that. Now, what is 1 revolution? 1 revolution contains 2 pi radians. So I must multiply that by 2 pi radians per revolution. You can see the 2 revolutions are going to cancel out when I come to the multiplication. I'm going to leave me with radians here. Then I've got to deal with the minutes get into seconds, and I know I've got to multiply by 1 minute is actually 60 seconds. So you're going to have 60 seconds per minute. That's why I can write it like that. Now if you look close, you can see that you've got the minutes cancelling out the minute. You've got the revolution cancelling out the revolution. And you get 6.2 times 2 pi radians, that's the unit for that, multiplied by 1, and you're going to be dividing by 60 seconds. So you can see we're going to have 6.2 times 2 pi times 1 divided by 60, and units are going to be radians per second. So we do the calculation, we end up with 0.649, and we've got radians, and we have got per second. Now we can change that to 2 decimal places, and we can say 0.65, and we can write then radians in the usual form. Since we're radians divided by seconds, is radians per second. We can write it as radians s to minus 1. That's the first answer. Question 2, part B. The microwave oven is switched off and the student places a P on the plate, 83mm from the axis of rotation as shown in figure 2b. The microwave oven is now switched on and the plate again rotates with an angular velocity of 0.65 radians per second. The P has a mass of 0.36 grams and follows a circular path. And for 3 marks, we're asked to calculate the centripetal force acting on the P. Well, if we bring in an overhead diagram of this, we can see that the P is sitting 83mm from the centre of a circle, and it's got a tangential velocity of V. Now to find the centripetal force, all we have to do is use the following equation. Centripetal force Fc is going to equal to the mass times the tangential velocity V squared, all divided by R, R being the radius. But we're not told what V is, so we have to exchange V for something else. But what we do know is that the tangential velocity V is related to the angular velocity with the following equation. V equals omega R. So we substitute V into the V squared, and we have the following expression. The centripetal force is equal to M omega squared R squared, and we've got to divide by that R. And we can see quite clearly that the R is going to cancel from the bottom, and we're going to have the final equation to be the following: M omega squared and R. So the centripetal force in terms of the angular velocity is M omega squared R. Now we know what the mass is, we know what the radius is. All we have to do is plug these numbers in, but we have to be very careful because the numbers are given, quantities are given in terms of grams and millimetres. So for example, the mass of the object, the P, is going to be 0.36 grams. Now to get into kilograms, we have to divide by 1,000, so that's the same as saying multiplying by 1 times 10 to the minus 3. So the shorthand we're doing to change from grams to kilograms is just to say 0.36 and multiply it by 10 to the minus 3, and we're into kilograms. The same thing happens for the radius. We know the radius is going to be the following 83 millimetres. So to change from millimetres into metres, we divide by 1,000. So that's the same as saying multiply by 1 times 10 to the minus 3. So we've got 83, and just add on to it times 10 to the minus 3. and you get your answer in metres. So we now have our data in the required units. All we have to do is plug them in. So the centripetal force, Fc, is going to equal to the mass, 0.36 times 10 to minus 3 kilograms. And we have to multiply that by the angular velocity squared. So that's going to be 0.65 all squared, 0.65 radians all squared. And then finally we've got to multiply by the radius, which will work out to be 83 times 10 to minus 3 of a metre. Now if you do that in your calculator, you end up with the answer of 1.94 times 10 to the power minus 5, and of course force is measured in newtons. So that is the centripetal force acting on the P. Part 2 of that first question for 1 mark, it says state the direction of the centripetal force. So we've got to our diagram. We know that the centripetal force always acts towards the centre, and therefore we can draw in the centripetal force acting on the P. If we draw the P here, at this position here, we know that the centripetal force is always going to act towards the centre, and we can draw it like that. There's the centripetal force acting towards the centre. So no matter where you are on that circular orbit, the P will experience a force towards the centre of its motion. So the centripetal force always points towards the centre. Question 2, continued part C. The microwave oven is again switched off, and the student places a second identical P on the plate, 120 millimeters from the axis of rotation, as shown in figure 2C. The microwave oven is switched on, and we have to explain for 2 marks why the second P is less likely to follow a circular path as the plate reaches an angular velocity of 0.6 radians per second. Let's take a look at the bird's eye view of that turntable, and here we have it here. We can see that P1, the first P, is at position P1, and that's got a radius, say, R1, which we know is equal to 83 millimeters. P2 is further out, it's got a radius of 120 millimeters. Now, we're told also it's an identical P, so we can assume then that the mass of the P is constant, so we've got the same mass. The angular velocity is going to be constant as well, because it's going to be 0.65 radians per second. So we know the following then: the centripetal force will just depend on the radius of the circle, because we know from our little equation that the centripetal force Fc is going to equal to m omega squared r. So if you've got the same mass and the same angular velocity, then it seems to be that force C, the centripetal force, will be equal to a constant times the radius. Or in other words, the centripetal force is directly proportional to the radius. Now what that really means is that the bigger the radius, the bigger the centripetal force is needed to keep that object going in a circle. So let's examine what we've got now then. We have got the following. We've got the P at position 2 has got a bigger radius, and therefore it requires a bigger centripetal force than P at position 1, because it's just situated at a bigger radius. So we need a bigger centripetal force. Now the centripetal force necessary for circular motion in this case must come from the frictional force between the P and the turntable. That's what keeps this P in a circular motion. The centripetal force comes from the force of friction between the P and the turntable. So why is P2 likely to fly off the turntable? Well, the simple answer is the following. The frictional force might be less than the required centripetal force. Therefore, the P will move off tangentially. So the frictional force between the P's surface and the turntable means that that only can provide that force for the centripetal force. But the further you move out, the P further moves out from the centre, it's going to require a bigger centripetal force, which might in fact exceed the frictional force, and therefore the P would be unlikely to keep in circular motion.